We spent a lot of time talking about light, and we've noted that in the old days, in the 1800s, light was thought of as waves, and that was due to primarily the work of Maxwell. But toward the beginning of the 20th century, we began to see light as having certain particle-type behavior, and this was due to the groundbreaking work of Planck, and in fact Einstein contributed a lot to this as well. So let's see if there's a way that we can make a similar kind of dichotomy for matter now. Okay, now when we talk about light, there are a couple of ways that we characterize light. For example, its energy could be characterized as h nu, and this is an example of how light may look like a particle, because this is the energy of a photon of light. But we also have this whole business of this nu being equal to the speed of light over lambda, or lambda nu time is equal to c, and these are manifestations of the wave-like nature of light. All right, so when we discuss light, both of these things are true about light, and so they sort of lead to a wave-particle duality in our picture of how light is depicted. Now, other work by Einstein, the work that he might be a little better known for, the theory of relativity, he was able to show that since light could behave as a particle, and I'm writing E photon here, since light could behave as a particle, that in fact the theory of relativity says something about how one could characterize its momentum. And in fact, one could write the energy of that photon as a momentum of the photon times the speed of light. So this P here represents the momentum of a photon. Okay, but we also know from this expression over here that we can relate light to its frequency. So in other words, we have a compound sort of equation now that Pc, which is the energy of photon, is equal to h nu. And h nu, in fact, is equal to hc over lambda. So if we set Pc equal to hc over lambda, and divide both sides by c, what we end up with is an expression that tells us how we can basically calculate the momentum of a photon based on its wavelength. All right, so this is a practical guide, if you will, for how to explicitly determine the momentum of a photon. Now, in case you're wondering, if we want to look at the order of magnitude of a photon, if we, for example, had ultraviolet photon of light, it would have a momentum that's something on the order of 10 to the minus 25 kilogram meters per second. Okay, now, is that very big or very small? Well, an electron traveling at something close to the speed of light would have a momentum of about 10 to the minus 22 kilograms. So it's appreciable, but it's still about 1,000 times smaller than an electron. So it's not a lot of momentum, and that's one reason why we don't typically think of light as carrying a lot of momentum. Okay, so now enter a very young physicist named Louis de Broglie, a French physicist, who was doing his PhD in 1924. In fact, this is all part of his PhD dissertation work. And what he was doing was looking at this result for light and asking the question, well, we think of matter as appearing as particles, but could it also be treated with this same sort of expression? So in other words, he essentially proposed, he hypothesized that we could relate the momentum of a piece of matter, a particle, as h over lambda, or in other words, we could define a wavelength for a piece of matter as Planck's constant divided by its momentum. And this was the de Broglie hypothesis. Now, in case you're wondering if this was a radical idea, in fact, he was in danger of not passing his PhD because of this idea, but his examining group sent his dissertation off to an eminent physicist who wrote back and said, this is the most brilliant thing I've ever seen, and they accepted his dissertation. It probably helped that the person they sent it to was Einstein, and Einstein was very impressed with what de Broglie had done. All right, so what we might ask is, why don't we observe matter as a wave? Okay, well, the momentum of a piece of matter would be the mass times its velocity, and we typically have mass that's about 1 gram. We have velocity, say, that's in centimeters per second, and so we would have, something on the order of we'd have something on the order of 10 to the minus fifth kilogram meters per second as the momentum for a piece of matter following this. Well, you can imagine that if we divide this into 10 to the minus 34, we'll end up with a wavelength that is about 10 to the minus 29 meters. Okay, not a very large wavelength. And this is why we don't typically see light, or we don't typically see matter as appearing as a wave. Okay, in fact, most pieces of matter are even bigger than this. Like a baseball, its wavelength is going to be perilously small. So what we might do is shift our point of reference to atoms. And for an atom, this has a mass typically of about 10 to the minus 27 kilograms. It might have a velocity, if we were in an ideal gas at some reasonable temperature, its velocity, say, might be something like 500 meters per second. And when we plug this into the formula that de Broglie devised here, so this formula, what we would find is that the wavelength would be something on the order of 10 to the minus 9 meters, or about 1 nanometer. All right, now this is getting closer to something that we could actually detect, but still very, very small. All right, similarly, we could look at the wavelength of an electron, or a small piece of matter, and it would have also a wavelength that's on this order. Might be actually a little bit larger than this. So how do we justify treating matter as a wave? Well, I want you to think about an atom and how big it is. What is the size of an atom? Well, it turns out that typically electrons around an atom are on the order of about 10 to the minus 10 meters from the nucleus. So you can think of it as a little sphere with a radius of 10 to the minus 10 meters. Well, if the wavelength of an electron is 10 to the minus 9 meters, that's 10 times larger. So in effect, what's happening is that atoms are so small that electrons really look like waves when you're at an atomic scale. And this also helps us to understand why, when we talk about matter at the scale of an atom or a molecule, we really need to take into account the wave-like nature of matter, because the wavelengths of matter are on the same scale as the size of the atoms and the molecules themselves. So this is why we're studying quantum mechanics this semester, so we can understand how to really define the physics for an atom or a molecule, which is, of course, what we're interested in as chemists.